Hello everyone, I am Yihong Sun and I'll be presenting our research project Dynamo-Depth fixing unsupervised depth estimation for dynamical scenes. In this work, we are interested in unsupervised monocular depth estimation, which is learning to estimate depth from single-view videos only without any ground truth labels. Typically, this task is formulated as a novel view synthesis problem with the underlying scene assumed to be static. Intuitively, the static scene constraint implies that the apparent pixel motion in consecutive frames is inversely proportional to the depth of the pixel, and that provides a useful supervisory signal for learning depth. However, the static scene constraint does not hold in general, and dynamical scenes with moving objects pose a significant challenge for existing methods. Here on the left, we show three input frames commonly found in everyday driving scenes, and here are the depth predictions by assuming a static scene. Notice that in the first row, the black van moving away from the camera is predicted to be infinitely far away, while the car moving towards the camera is predicted to be floating in midair. In both instances, the depth network explained their independent motion by placing them at incorrect depth to generate the correct rigid flow for reconstruction as shown in the middle. Additionally, incorrect depth predictions for moving objects are also present in the second and third rows. And to mitigate these errors and ensure reliable navigation around moving objects, we propose Dynamo-Depth, which improves depth estimation for dynamical scenes by modeling 3D independent flow and motion segmentation. As shown, Dynamo-Depth is able to predict the correct depth for moving objects by explicitly disentangling their independent 3D motion from the ego camera motion-induced rigid flow. Architecturally, Dynamo-Depth is composed of two components, the rigid motion networks and the independent motion networks. First, the depth network predicts a monocular depth from the target frame I sub t. Then, the ego motion networks predicts the camera transformation from target frame I sub t to source frame I sub s. By combining the two, we compute the rigid flow Fr, which models the ego camera motion-induced 3D flow field. Similarly, the complete flow network predicts the complete 3D flow field Fc along with the motion segmentation M predicted by the motion mask network. From this, we compute the independent motion field Fi as the difference between the rigid flow Fr and the complete flow Fc gated by the motion mask M. Finally, we combine both flow fields Fr and Fi to reconstruct the target frame I sub t hat by sampling the source frame I sub s. Here we offer our key insight that a good motion mask estimate would disambiguate apparent pixel motion, which allows depth to be learned on static pixels and independent motion to be learned for the dynamical pixels. And to correctly learn the motion mask network, we propose a novel initialization scheme that stops depth training early, and this separates learning into three stages. In stage 1, we initialize the depth and ego motion network without the independent motion networks. Then, at an early iteration, we freeze the rigid motion networks and initialize the independent motion networks via the same objective. And finally, we fine-tune all models jointly end-to-end till convergence. Here, in addition to the target reconstruction loss term, we introduce a motion consistency term that penalizes any inconsistencies between the rigid flow Fr and the complete flow Fc, where the motion mask M is not active to further constrain the learning for the complete flow Fc. Here we plot the absolute relative error for the Waymo Open dataset, and to demonstrate generalizability of the proposed framework, we adopt the depth networks from two separate approaches, namely Mono-Depth-2 and LiMono. By leveraging the semantic and 3D annotations, we evaluate performance on four different splits, namely all regions, static backgrounds, static objects, and moving objects. Notably, our proposed method reduces error across the board with significant relative error reduction of 68 and 67% on moving objects compared to the Mono-Depth-2 and LiMono baselines respectively. Here we show qualitative results of Dynamo-Depth, where the depth of moving objects are predicted accurately along with correctly predicted independent motion and motion segmentation. Specifically, Dynamo-Depth is able to recover and model small objects in the top row, accurately model independent motion during camera rotations in the middle rows, and predict accurate estimates where independent motion is extensive in the bottom row. For more results and code, please visit our project page. Thank you for listening.